Welcome to the lesson on section 5.3, the Fundamental Theorem of Calculus, Part 2. In this lesson, you'll learn how to evaluate definite integrals algebraically using an antiderivative. In class today, you learned about Part 1 of the Fundamental Theorem of Calculus. That part of the theorem tells you how to take the derivative of an integral. The second part of the fundamental theorem says that the definite integral of f from a to b can be evaluated as the difference between the values of an antiderivative evaluated at a and b. Since this works for any antiderivative of f, we'll choose the antiderivative in which the constant plus c is 0. It's not at all important for you to know which of these is part 1 and which is part 2. In fact, different textbooks may not be in agreement about the numbering of the two parts of this theorem. Now let's look at the proof of Part 2 of the Fundamental Theorem of Calculus. Let the function capital F equal the integral from a to x of little f of t dt, and the derivative of capital F is little f from the first part of the fundamental theorem. Then g is equal to capital F plus a constant. That represents any other antiderivative of little f. G of b minus g of a is equal to f of b plus c minus f of a plus c, which simplifies to f of b minus f of a. Substituting from our given conditions, f of b means the integral from a to b of f of t dt, and f of a is the integral from a to a of f of t dt. The integral from a to a is 0, so the integral from a to b of f of t dt is equal to g of b minus g of a, where g is any antiderivative of little f. Here are some examples. To find the integral from 2 to 4 of x minus 1, first find an antiderivative. 1/2 x squared would have x as its derivative, and negative x would have negative 1 as its derivative. Since we can use any antiderivative, we'll use the one in which the constant is 0. Now we need to evaluate this function at 4 and 2 and find the difference between these values. Use a vertical bar with a 4 and a 2 to symbolize this. Plugging in 4 and 2 for x, we get this. And simplifying gives us 4. In part b, to find the integral from 0 to 2 pi of the sine of x, first find an antiderivative, and find the difference between its values at 2 pi and 0. The value of this integral is 0. Similarly, to find the integral from 2 to 3 of x to the third, an antiderivative is 1/4 x to the fourth. In this one, I'm leaving the 1/4 aside and evaluating x to the fourth at 3 and 2 first. In part D, we don't know how to integrate sine x to the fourth without a calculator. The function negative cosine x to the fourth would not be an antiderivative because we would need to use the chain rule to find this derivative, and the necessary 4x to the third is not present in the integrand. Negative cosine x to the fourth divided by 4x to the third also would not work because we would have to use the quotient rule to find its derivative, and this would not come out to sine x to the fourth. Here's how to use a graphing calculator to evaluate this integral. Press alpha F2 and select number 4, function integral. Enter the problem exactly as it appears on the screen and press enter. To 3 decimal places, this integral is approximately equal to 0.009. If you were following along on your calculator and didn't get this answer, Check to make sure your calculator is in radian mode. In this problem, we won't be able to use the fundamental theorem to evaluate the integral. Recall from an earlier slide that the integrand must be continuous on the interval from a to b. Here, the function 1 over x squared is not continuous at 0, which is somewhere between -1 and 1. We'll have to revisit this problem in a later lesson. This concludes our lesson on section 5.3, part 2 of the fundamental theorem of calculus.